In the previous video, I defined the supremum and the infimum of a set. It's linked in the description. In this video, I will define the supremum and infimum of a function instead. This is actually an easy concept if we already know what the supremum of a set is. When we talk about the supremum of a function, we simply mean the supremum of its range. That's it. I could pretty much end the video here, but let's elaborate a bit. To calculate the supremum of a function f on a domain I, this is sometimes implied. If we do not specify the domain, we mean on the full domain. First, we need to construct the range. Here is the range described in set builder notation in red. It is the set of elements of the form f of x, where x is in I. This is a set. And then I simply take the supremum of this set. That's it. There is an alternative piece of notation to describe the same number. Sometimes people will write this as sup of f of x, and as has happened of sup, x is in I. This expression box here in blue is just new notation to mean exactly the same as the line above. For example, consider the function f defined by this graph. I want to compute the supremum of f on the interval -2, 2. I need to restrict the function to the domain -2, 2, so I keep only the piece of the function represented by this part of the graph, and the range is the interval -1, 1. Therefore, what I need to compute is the supremum of the interval -1, 1, which is 1. That's all. Now, this is how I define the supremum of a function, but I can define many other concepts in a similar manner. I can define upper bound of a function, or maximum of a function, or infimum of a function, or other concepts. And whenever I say of a function, I always mean of the range of the function. Let's look at another example. Consider the function g defined by this graph. G is bounded above on the interval 0, 2. The supremum of g on the interval 0, 2 is 1, but it has no maximum. On the other hand, if we look at lower bounds instead of upper bounds, we can see that g is also bounded below, and it has an infimum, -1, which is also a minimum. To conclude the video, I want to mention two important theorems. First, there is an immediate consequence of the least upper bound principle, which we already know. The least upper bound principle is about sets, but we can extend it to functions. The theorem says that if a function is bounded above on a domain that is non-empty, then it has a supremum. The second theorem is an old friend we know very well, the extreme value theorem. I remind you of what the extreme value theorem says. If I have a function defined on a closed and bounded interval a, b, if the function is continuous, then it has a maximum and a minimum. Notice that the two theorems are related. They both offer a sufficient condition that guarantees that a function will have a supremum in the first case, or a maximum in the second case. That is why I like to look at the theorems side by side and why I mention them in the context of this video.